Hello students, and welcome back for our second and final lecture video of this week about carboxylic acids and their derivatives. So in the last lecture we covered the reaction of acid anhydrides and also esters. So now we're going to go to our least reactive group, the amides. So notice that in the reactions that we have seen before, we can convert acid chlorides to any of these other groups, and then because these are the most reactive here, and then we were able to convert anhydrides to esters or to amides. We saw how we can convert esters to amides as well, and now we have our least reactive group, amides. And so what can be done with these amides? Let's take a look at the reaction of amides. So first of all, we saw how we could produce amides by the reaction of acid chlorides with two equivalents of ammonia, where ammonia behaves as the nucleophile, and the reaction begins with the nucleophilic attack of the ammonia on the electrophilic site here, the carbon attached to the oxygen, the carbonyl. And remember that two equivalents are necessary because one is required to attack and the other one is neutralized by the HCl byproduct here. So amides can be hydrolyzed with exposure to acid and to heat, and we can return to our carboxylic acid from the amine. However, the reaction is slow and requires high temperatures. The reason being is we've got a big activation energy barrier here to go and produce this carboxylic acid. Even though there's a kind of stability to it, the amide also being the least stable too, though we still have a significant energy barrier which slows the reaction down. So amides can be hydrolyzed, as we said, again, under acidic conditions. The products here are favored at equilibrium because the ammonia group here is protonated and it's not capable of acting like a nucleophile. So what happens is this reaction is driven forward by the fact that the amine that's produced by this hydrolysis is then protonated and can no longer behave as a nucleophile and go backwards and attack the carbonyl carbon. And so that makes the whole product, the set of the two products here, more stable than the reactants. So in terms of how this reaction occurs, note that this is a reaction that's occurring in acidic conditions. So in acidic conditions with these carbonyls, the first step, as we have seen, has been the protonation of the carbonyl by reaction with the acid. This is going to produce for us a protonated carbonyl with the carbon having a double bond and one bond to hydrogen, one lone pair, because it had two, it gave one up to make the bond with the hydrogen. And so now it has a positive formal charge. And now that this carbonyl is protonated, that makes it even more susceptible to nucleophilic attack. So even a weak nucleophile like water and alcohol can very easily attack this carbonyl, and we then have this resonance arrow here putting the electrons up on the oxygen. That gives this oxygen now two lone pairs and one bond to carbon, one bond to hydrogen, so no formal charge. However, we did have an attack by a neutral nucleophile, and so that means that this water now, this oxygen, this lone pair was used to create that third bond. So it has three bonds and one lone pair, giving it a positive formal charge. So the next step in the mechanism, as we saw with the hydrolysis of the esters, essentially a completely analogous situation with a little bit different at the very end here. We have the deprotonation of the alcohol here with the water, and so the water grabs a proton. These two electrons are left behind, making this group now a hydroxyl group or an alcohol group. This amine now can be protonated by the acidic environment, and so whereas before we had an amide, now we have an amine. And the amines behave as bases, so in an acidic environment they're going to accept a proton from the acid here. And note that this acid was recovered. This is catalyzed by the acid because this acid is recovered in this step here, right? And then it's used to protonate the amine. And finally, we're going to have the loss of the leaving group now as a neutral ammonia. So we're going to have this arrow here come back, create these lone pairs now become pi electrons in a carbonyl bond, while we simultaneously have the loss of the ammonia leaving group. And because it's protonated, so it gets protonated so it can leave as a neutral ammonia. But at that point, we again have this oxygen making a double bond with one bond to hydrogen here and one lone pair. So that means that it's a protonated carbonyl. So at that point, it could be deprotonated. It could be deprotonated to some extent by water, but it will be much better deprotonated by the ammonia that was just formed when this NH3 group left as a leaving group. So this grabs the proton, these two electrons being left behind, recovering our deprotonated carbonyl, and then getting here a protonated amine, which is no longer a nucleophile. So this reaction is unlikely to go backwards. This drives this reaction forward to completion, and now we have hydrolyzed this amide and have gotten ourselves an acid and ammonium ion in this acidic environment. Now, amides can also be hydrolyzed under basic conditions, and our same rules apply here. To remember, when we have acidic conditions, okay, generally we're starting with the protonation of the carbonyl. In these basic conditions, you're not going to be protonating anything. There's not extra protons lying around. And so this one is going to go on with the hydroxyl group behaving as the nucleophile and attacking the carbonyl carbon here, the nucleophile, the electrophile, and then we have the resonance arrow here leaving this oxygen with one bond and three lone pairs, a negative formal charge. So remember, the rules about these base reactions is that they should not have positive ions in them, right? They should be negative ions, and there should not be things that are protonated by anything. And notice that we will use acid at the end, but that's going to be in a second workup step that occurs after we have isolated the carboxyl ion and need to protonate it. So this mechanism is exactly analogous to the base catalyzed hydrolysis of an ester. So we're going to see the same type of thing, the nucleophilic attack by the hydroxyl group. We have then the resonance arrow. As I said before, we have the alkoxide ion. And now in this case, we're not going to have, like we had before, protonation of the amine and its loss as a leaving group that was neutral, right, as NH3. Here it's going to leave as a amide ion, hugely basic. Okay, so you might think this is not stabilizing the negative charge very well at all. Well, that's true, but it's going to get immediately protonated by the carboxylic acid that forms, because now we have the carbonyl being recovered here, so we can see that this oxygen here is now going to have a double bond to the carbon, and it will no longer have three lone pairs, it will only have two. And so what that's going to do for us is get us our carboxylic acid, because we still have this alcohol group here attached to the same carbon. So now this can very easily be deprotonated by this very strong base. It's going to grab that proton and give us ammonia, and then we're going to have this oxygen here with three lone pairs and one bond, and so it has a negative formal charge. And notice that this is a much more stabilized negative formal charge, being a part of this ester. And so this reaction, the fact that it produces this stable carboxylate ion here will drive this reaction forward. Notice that this is negative, so it's not going to be as nucleophilic too, so we don't have to worry so much about the ammonia attacking as a nucleophile here. Amides can also be reduced with lithium aluminum hydride. However, the reduction proceeds in a way that's different from the other reactions. The carbonyl group is completely removed and replaced with hydrogen atoms, and we still have the amino group here. Note that the mechanism is not provided for this reaction, and so generally that's an indication that it's not very well understood, or not sure, they're not sure about it. But it does not proceed in a way, obviously, that is the same as the others, because in those the carbonyl is recovered, but in this one it is not. So that was our reactions of amides. Now we're going to talk about our reaction of of nitriles. So first of all, recall the formation of nitriles. Nitriles can be formed by SN2 reactions with the cyanide ion as the nucleophile. We also have the sodium ion here, but we don't really care about that. What we care about is the cyanide ion, and that's going to, on this, we have here a primary alkyl halide, so this is very good for SN2 reaction. We have an attack by the cyanide and a simultaneous leaving of the leaving group. And notice what this does for us. This adds for us an extra carbon atom on, one more carbon atom. So when you're doing synthesis, you want to think about the fact that reaction with the cyanide ion does add on a carbon atom like this, right? And nitriles can also be made by the dehydration of a primary amide using SOCl2. We're going to talk about that mechanism, but remember, whenever we use SOCl2, what's been the key feature of this SOCl2 is the sulfur that's double bonded to the oxygen here. The thionyl chloride, as this is called. And what this gives us is quite a polar bond here, where the sulfur, just as much as a carbon, perhaps even more so, is a significant electrophile. And so what we're going to have is these pi electrons, which are nucleophiles, will be free to attack, and that's going to begin the beginning step of this. So this is very common for when we're using thionyl chloride as a reagent, right? Ultimately, we end up with SO2 gas being released, and so the sulfur releases completely, and we end up with a triple bond between the carbon and the nitrogen, giving us a nitrile. So let's take a look at this mechanism here. We've seen an analogous mechanism before in the previous chapter. We have, again, these pi electrons here are going to go ahead and attack this electrophilic center right here, and will behave as a nucleophile in this case, and we'll have these electrons here. We'll draw a resonance arrow to put them on the oxygen. That gives this oxygen 3 lone pairs and 1 bond, giving it a negative formal charge. Simultaneously, we also have a formation of a pi bond between the carbon and the nitrogen here. So these electrons are delocalized, right? I mean, we could also write just resonance arrows here. These electrons are not, they're not localized electrons, they're delocalized with resonance through this carbonyl. But at this point, the nitrogen will be making 4 bonds with no lone pairs, so it will have a positive formal charge. At that point, we're going to get a loss of a chloride as a leaving group. So we get the recovery of this sulfur-oxygen double bond and a simultaneous loss of the chloride as a leaving group. And so now we have this sulfur here with a double bond to the oxygen and a bond to the chlorine here and a bond to the oxygen atom. Okay. And so now at this point, we're going to have the introduction here of a base of some kind. So under a basic environment here, this positively charged nitrogen can be deprotonated. And so we have a proton transfer. That ultimately gives this nitrogen now 3 bonds and 1 lone pair. So it now again has no formal charge. But at that point, we're going to now expel the SO2, and this is going to be by a second deprotonation of the nitrogen, which is then going to result in the formation of our triple bond, while we simultaneously lose the SO2 and it loses its chlorine leaving group. And so at that point, we get another chloride ion here. We get this part here leaving as SO2, and now we have this carbon, which is triple bonded to the nitrogen. And so effectively what occurred was that we replaced the whole carbonyl group here with a carbon triple bond to a nitrogen. So likewise, we can do the reverse, and we can hydrolyze the nitrile, and we can get an amine back, and we can further hydrolyze the amine and get a carboxylic acid. The nitrile is hydrolyzed again to the amide here. I said amine, sorry, to the amide, and then further hydrolyzed to the carboxylic acid. So the mechanism for that, notice that dehydration. Oops. So in addition, besides acidic conditions, this can also be done under basic conditions. So we're going to look at this mechanism, this hydrolysis of the nitrile under both the basic conditions and the acidic conditions. So under the basic conditions, let's think about this bond in a nitrile. This bond is a polar bond, okay? The electrons are being drawn from the carbon to the nitrogen. The carbon has a higher electronegativity. So it's partially negative by the carbon and partially positive by the or partially negative by the nitrogen and partially positive by the carbon. So what this means is that the carbon is going to be an electrophile. So we can have a nucleophilic attack on the carbon, and we can't have 5 bonds on the carbon, so we have to simultaneously here have a resonance arrow from one of the pi bonds here to the nitrogen. And so that reduces the triple bond here. Now it's not a triple bond, it's a double bond now. And there are 2 lone pairs in the nitrogen, so it's making 2 bonds and has 2 lone pairs, giving a negative formal charge. And now this carbon is attached to an OH group, so it's an alcohol. And now this nitrogen is going to be extremely basic. We know already ammonia is already quite basic. This is going to be like an amide ion, a nitrogen with a negative formal charge. It's going to be extremely basic. So it can definitely deprotonate water here as the solvent, or the water that's, that this is all dissolved in. And so we have a proton transfer here where this nitrogen grabs this hydrogen, and we recover our hydroxide. So remember, this is base catalyzed, so we recover the hydroxide in this reaction here. And at that point, the hydroxide then will then grab the proton from what is similar here to like a carboxylic acid. We'll have a proton transfer here, and this will then create this negative oxygen here, the oxygen with the negative formal charge. It has now 3 lone pairs and 1 bond. And now we can write a resonance arrow here where we have this delocalized electron pair being written as a pi bond. Likewise, this electron pair is delocalized. This one's delocalized because it's allylic. We have an allylic lone pair, so it's delocalized. Here we have a pi bond between 2 atoms of differing electronegativity. This nitrogen atom here now has 2 lone pairs and 2 bonds. Again, hugely basic. So now it will go and deprotonate any water as the solvent, and we'll grab that hydrogen, and now we have the amide back. And so that's how we do the hydrolysis of the nitrile under the basic conditions. And so the reaction here looks as so. Notice finally we could follow up with an acid to make sure, whoops, what happened here? Sorry, we can follow up with an acid to make sure that the carboxylic acid is protonated at the end. Or rather, we can follow this up with treatment with an acid to hydrolyze the amide and ultimately get us the carboxylic acid. Otherwise, the basic conditions would give us a deprotonated carboxylate ion. So under acidic conditions, the way this would work is the nitrogen will behave as a base, and so it will grab these protons here from the water in a proton transfer from the hydronium ion rather, and we have a protonated amide. Notice that here we're having a weak nucleophile attack. So the protonated amide basically means that because this nitrogen has this positive formal charge, the electrons are going to be even further withdrawn from the carbon, giving it an even more positive charge. And so the result is that it's going to be even more susceptible to a nucleophilic attack, much in the way the protonated carbonyl would be. And then we have again the resonance arrow here showing these pi electrons in the nitrogen atom, a pi bond between 2 atoms of differing electronegativity. Next, we're going to have a deprotonation, and we're the deprotonation of the water, because now notice that this water attacked here, it now is making 1 bond to the carbon, and it has 2 other bonds to hydrogen and 1 lone pair, so that gives it a positive formal charge. And so we'll recover our acid. Remember, this is acid catalyzed, and so the acid here is recovered by the deprotonation of that water that attacked by another water. and that means that these 2 electrons will then return to the oxygen, and we have a oxygen with 2 lone pairs and 2 bonds, making it 0 formal charge here. Now this, again, we have acidic conditions here. We have recovered our acid again, and so this acid can now be used to protonate the nitrogen, quite basic, as nitrogen atoms generally are. And we're going to now have the protonation of that. And so we have the protonated nitrogen, and we've got 4 bonds now and no lone pairs. And so that gives it this positive formal charge. And now we have a pi bond here that's adjacent to a positive formal charge. So we have that resonance arrow here. We also have an allylic lone pair here. And so that's going to give us here this carbon double bond to the oxygen. Now it only has 1 lone pair, so it has a positive formal charge. This nitrogen now has 3 bonds and 1 lone pair drawn, so that's no formal charge there. Finally, this protonated carboxyl group here can be deprotonated by water recovering our acid catalyst and then returning this oxygen to having 2 lone pairs and a double bond. And now we have the amide. So we've hydrolyzed the nitrile to get the amide. We can also use Grignard reagents as nucleophiles. Again, the nucleophiles are going to attack the carbon that's in the nitrile. So here we have the attack of the carbon in the nitrile. That's the first step, and the resonance arrow putting 2 lone pairs on the nitrogen and having a double bond, so that gives it a -1 formal charge. And so we can see this is kind of analogous to what we just saw. After the nitrile reacts with the Grignard, we add in acid here, and we form an amine, which is hydrolyzed with excess hydronium in the ways we've seen before, ultimately to form the ketone. So again, also with nitriles, we can react them with the reducing agent, and just like the amides, what we end up with is just this carbon atom here that was in the carbonyl before. When we had the amide, it would get 2 hydrogens, and we kept the amino group, right? And the same thing here. This carbon is going to get 2 hydrogens attached, and we're going to keep the amino group. And again, this mechanism is not completely understood, so you're not going to be provided a full mechanism for this one. So now, as you've seen, we've learned a lot of reactions in these last few chapters, and this one in particular with these these carboxylic acids and their derivatives. So we're going to keep asking ourselves the same 2 questions when we start a synthesis problem. Is there a change in the carbon skeleton? Are we adding on more carbon atoms? And let's take stock again now. We've got some new ways of adding carbon atoms that we didn't have before. With these reactions of acid chlorides and so forth. So which reactions here do we have that can change the carbon skeleton now? We have some new ones. Also, are there changes in functional groups? So we saw a lot of changes in functional groups in this chapter. We saw changes between acid chloride and acid anhydride and amide or esters and amides and nitriles. So what functional groups are we creating with each of these? And we're going to want to incorporate this into our reactions that we can use to achieve particular functional groups in our final product. So here's a summary of synthesis strategies that are related to this chapter. Now note that the way this is laid out is that from top to bottom here, this is the most oxidized. So up here is the most oxidized form, and going down is being reduced here. The most oxidized form being the carboxylic acid, which we can reduce here to these carboxylic acid derivatives, which are actually the same oxidation state on the carbon here, but we can reduce these further to aldehydes here, and finally to alcohols, or to amides and down to amides by adding more hydrogen atoms on. Notice that all the time when we're reducing, we have sources of hydrogen atoms like lithium aluminum hydride, or DIBA, which is that lithium aluminum hydride, but it only has one hydrogen instead of four, and it has two large bulky groups attached. Or we can have a lithium aluminum hydride, but again, with the other groups replaced, with the hydrogens replaced with other ether groups here. And so these are all reductions here. And we can oxidize the alcohol all the way up to the carboxylic acid with a very strong oxidizing agent like sodium dichromate in sulfuric acid and water. Note that we can't directly reduce a carboxylic acid to an aldehyde by using lithium aluminum hydride because it is too strong of a reducing agent. It will reduce it all the way down to the alcohol. If we want to reduce it to an aldehyde, we'll want to go through one of these steps where we'll make one of these carboxylic acid derivatives like an ester here or a acid chloride, and we can then reduce that to produce for us our aldehyde. And then when it comes to all of these reactions, note that they all use this, they can all come from the carboxylic acid, right? And they're using similar reagents here. So we can get any of these functional groups that we need synthetically from the carboxylic acid or from one of its derivatives using these reactions. When it comes to deciding, are we adding more carbon atoms? So one of our ways of adding carbon atoms has been for quite a while now the reaction with a Grignard reagent, which in the case of a carboxylic acid derivative like this will add two groups with carbon atoms and ultimately produce for us the alcohol. So when you're looking at something where you have the alcohol as a product and you have additional carbon atoms on, you should be thinking about a Grignard, right? That definitely might work there. Remember, the other one that we had that's not related to this chapter is the deprotonated alkylnide. If we take a primary alkyne here, and we react with excess with NaNH2 in ammonia as step 1, and then we react with step 2 with some alkyl halide, we can add these carbon atoms on. So that was one that we didn't learn in this chapter. But this is another valid option here. If we want to reduce just to a ketone here, we can use this Gilman reagent which is similar to a Grignard but with copper atom here, and two of these R groups here. And finally, we have a new one now. We can react a nitrile here with a Grignard, and we can ultimately get for ourselves a ketone as well. We have to ultimately introduce acid to protonate the amide that's formed here, so that the reaction does not go backwards. Okay. And some other carbon-carbon bond forming reactions that we've seen recently, when we were talking about the reactions of carboxylic acids in this chapter, we said we could also react an alkyl halide here, make it a Grignard reagent, react it with CO2, and the carbon being the electrophile here for this Grignard, and the Grignard being the nucleophile, and then we can produce a carboxylic acid, ultimately protonating that carboxylic acid with some kind of acid, which we can just indicate as H3O+. In addition, we can add an extra carbon atom on by reacting an alkyl halide with sodium cyanide, as we just reviewed. And so we've got a few different new ways of adding carbon atoms. So that's something I always look for first. I look for, do I have more carbon atoms on this molecule? If so, I start to consider one of these reactions as a part of my synthesis. If not, I just think, well, what can change this functional group to the one that I want? Now, when you're installing functional groups, remember there was another way that we had here to add carbon atoms, and that would be the reaction of some nucleophile with an epoxide, which ultimately gets for us a chain with more carbon atoms and an alcohol as well. So this will move the functional group over as well, so that the nucleophile here attacks would ultimately, when we produce this Grignard reagent, we're going to have R minus and Mg Br with the plus, and this is going to go and attack here at the less sterically hindered primary position, and we'll have the opening of the epoxide. Ultimately, we'll need the acid to protonate the alkoxide ion. But what we can see here now is that this alcohol group is over here on this carbon number 2 relative to the carbon number 1, where that was attached to the additional carbon chain. So here we're adding carbons, and the alcohol group is not where we added the carbons. It's 2 carbons away, 1, 2. So think about where you want the alcohol to go to if you're adding carbon atoms and you're producing an alcohol. If you want the carbon atoms to be added at the same carbon as where the alcohol is, you're going to want to use the Grignard reagent on the carbonyl. However, if you want to add the carbon atoms on a carbon that's 2 away, then you're going to prefer the reaction of an alkyl halide with an epoxide, as we learned in chapter 12, or 13 rather. Finally, having to do with spectroscopy. And so we've already studied NMR spectroscopy. This is a reminder for carbonyl groups that we have always in IR, we always have a stretching frequency in the region of about 1650 to 1800. And the exact frequency of the peak in the IR will depend on the nature of the particular carbonyl group that we have. If we have an acid chloride, that tends to have the highest wave number. Acid anhydride's a little lower at about 1760 and 1820. Here with 2 signals, the 1820 being higher, the 1760 being lower. Carboxylic acid is also around 1760, and ester is about 1740. A ketone around 1720, and an amide here around 1660. And notice and remember that what we have here is these conjugated carbonyls. When they're conjugated, that spreads out the electron density, right? And so here we get these lower and lower, wave numbers here for these guys. So in terms of the IR spectroscopy, the OH in the carboxylic acid gives a very huge broad peak that tends to overwhelm the CH stretches as well. And so it's a very distinctive peak. When we have the carbon-nitrogen triple bond, that occurs around 2200 in the triple bond region, and so that's another peak that can be picked out indicating the nitrile. Carbon-13 NMR peaks are going to be very downshifted at about 160 or 185 because of the nature of that polar bond there, for the de-shielding rather that occurs for these carbonyls here. The nitriles are going to be at a kind of intermediate downfield position at 115 to 130. The proton for the carboxylic acid appears very downfield at around 12 ppm. And so that's just a quick review of the IR of these. And so that's going to conclude the material here for chapter 20. Make sure to practice, and I'm going to be assigning some synthesis problems as well. These are going to be great for integrating these reactions into the body of other reactions that you know. And so good luck with those, and when you get really stuck, you can peek at the solutions, but you want to make sure that when you're getting close to the test, you can do these homework problems and other synthesis problems if you need to do more, like other ones that are in the chapter that have the answers as well. But at least do the ones I've assigned for homework, and make sure you can do those without peeking. and make sure that you understand why each step occurs, keeping in mind, when you have these acid catalyzed mechanisms, that you tend to have protonations. You don't have deprotonated alkoxide ions and things that can only exist in basic solution, because they'd be deprotonated by anything they would be protonated by anything that's decently acidic. Also, when you have basic conditions, remember that you'll often have deprotonated ions, right? Negative ions. And so those will be the differences between those types of mechanisms and one another. So good luck with your studying, and please let me know if you need any help, and have a great week.